So let's get into what is a big, what are the important parts of a motion system, and kind of what are the things you're trying to pick. Let me give you the big picture first about motion control. So somewhere generally, I'm just going to draw it as, you know, we've got some mass that we're trying to move around. It may or may not be, it may be some combination of multiple masses. And actually, a lot of times what actually happens is, here's the one that you really want to make, you know, that's the thing that you really need to move, but you end up moving things that are all sorts of other components that weigh a lot more just to move the one thing you really want to move. So the first thing you start thinking about when you're designing mechanics is weight matters, mass matters, inertia matters, but also thinking about how to move the load that you really want to move and not have a whole bunch of other stuff that you want to move. You know, robot arm is a great example. If you think about what you're picking up with the robot arm, you're picking up some little part and putting it over here, you know, back and forth. And even my hand, I'm watching my hand in my picture and it's zooming around. Well, that's what robots do. They zoom around and they move way faster than humans can really even see, and they go way more accurate than you can. How can it do that? If you ever watched that machine where it starts moving and then pretty soon it starts going faster and faster and doing it, and pretty soon it's a blur. But so there's always this human rate that we can see, and then there's machine rate. When you're doing your proof of concepts, you're going to be having to even bring things back down to the human rate, so that your audience can understand that you actually proved the concept. Sometimes if you make it go at full speed, they can't see anything. They can't process it. You can't see it fast enough. But it's a common thing when you think about how much mass is moving with the robotic arm just to make the thing that the gripper picked up. And it's, what would you say, 100 to 1 mass of the robot compared to the mass of the object that you're picking up. Think about just you getting in your car coming over here. How much do you weigh? 200 pounds. What was the weight of the vehicle? 4,000 pounds, right? So you move 4,000 pounds around, 4,200 pounds to move 200 pounds. But nevertheless, what do? You go out and get in your car. Why? It's got a heater. It's safer, probably, right? But anyway, it's something I think about. Even like back in O'Connell, when we used to be there, you'd go in the elevator. How much does that elevator weigh? I don't know, 2,000 pounds? To do what? Move you up because you're too lazy.
More than me.
Take the stairs, right? It happens over and over and over. That's all I'm saying is that. And so one of the things you're looking at as you have to look at the mass is, design wise, minimize the mass, obviously. The next thing in the picture is not the motor moving the mass around. The next thing in the picture, I don't know how to draw. I guess I'll just draw it as, you know what, I'll draw it as this nice blue spring. Okay, what I drew is, these are spring constants. Now, in the controls class that you took, they taught you to go look up that spring constant, and you started to do transfer functions. And you actually use these spring constants to try and figure out what was actually going to happen when over here, the next thing here, we have motor. The trouble is, between the motor and the mass is always some sort of spring constant. I'll get into it later when we get into servos, but this is the problem with motion control. You have control over that, and the only way, but what you're really after is controlling that in space. And what you have control over is the motor. And there's a bunch of mechanics and a bunch of mass, and sometimes there's friction. You got stuff, all the standard mechanical stuff that you have going on to get this mess. But the goal is we want to move that, and you get to move that. And you don't even get to move that. You get to tell that to move, and you have to use electromagnetics, which are squishy, right? It's not a gear tooth on a gear tooth. That happens out here. At the motor level, all you get to do is really control the current in a winding and hope it creates magnetics. And there's a whole bunch of things that happen there. So you're losing control by many degrees about being able to control that point. So the trick of all this mechatronic design is how do you figure out each of these pieces so that you don't spend too much, but you don't lose too much. That's the tricky part of the design. So when we're dealing with motors, we've got probably 3 main types of motors. The first one we're going to deal with in the first part of this, would you just please stay there? Stepper motors. Now, whether you call it stepper motor or a step motor, either one is fine. Doesn't matter. So stepper motor, there are brushed and there are brushless. Sometimes you'll see the word DC motors. Sometimes you'll see AC servo. There's some things that you don't really care about because actually most of the time what you're going to care about is how much speed, how much torque, and what does it do with velocity and position. What is in the motor that we've got to deal with? Well, we know it's a coil wire, right? So we got a coil wire, and the first thing we're trying to do, the first most important thing, trying to make an electromagnetic field. Magnetic field. So you guys maybe studied electromagnetics. There's, the strength of the field, the number of turns has to do with basically this, the whole idea in this motor is you've got a coil, and then at some point you have a magnet with a north and a south on it. And you're trying to make a magnet move back and forth with an electromagnet. And with some constraints of bearings and shafts and that kind of stuff. But that's how you're moving mass around, is you're moving mass around with electromagnetic fields. So what are the things that happen with the electromagnetic field? That's obviously, that's good, right? So what do you, if you want to make a stronger and strong, you can buy strong magnets, right? So when you go to buy a motor, you can choose the cheap motors, they use cheap magnets. The more expensive motors that have more torque use neodymium magnets, or even who knows what better ones than that at this point. I don't know. I haven't been keeping magnet technology, but you can buy lots of different levels of magnetic strength in the same size of magnet. So there's a choice that the motor manufacturer made. Now, he's going to put some coils in there. What makes an electromagnetic field stronger? What do you do to make a strong magnetic field? You have control over what 2 variables?
Voltage and current.
Voltage you don't care about so much. You do a little, well, okay, yeah, I'm going to go with voltage in 1. That's going to affect us a little bit later. The electromagnetic field isn't proportional to the voltage. The voltage has more to do with how the current changes, right? So current is what you have control over. So current in that is, I believe if we go back to that BH squared or something, that I think current is pretty proportional to the strength of the field. So you've got control over that. And one other thing that the motor manufacturer is controlling: current and voltage. And so here's the voltage and current you need to give to this motor. There's one other thing when you've got a winding that controls the strength of the magnetic field.
Number of coils.
Number of turns, right. number of turns or coils, however you want to put it. Yeah, how it's wound. And so the more windings you put in this thing, which windings equals either big wires and fewer turns, or little wires and more turns, or just more turns is more mass. So there's a balance there, but you have control over that. So the the manufacturer controls this and that. He tells you how much current to put in it, and here's the strength of the field that they wound it to. Okay, so it makes an electromagnet. That's good. Any downsides to an electromagnet? There's one downside. Remember this guy? Did you guys have that? Did you?
Lenz's law.
Yeah, you go through that sum point, right? Like 4C, physics 4C. Is that where you get that? Something like that. And Lenz's law basically makes this thing kind of tricky to use, because on one hand, if it's static current going into the winding and it doesn't change, then you get an electromagnetic field. But what happens as soon as you start to change the current in the winding? What do you get?
An induced magnetic field out of the current that's changing?
Kind of. Do you remember that word back EMF voltage? You ever hear that? Back EMF voltage? Okay. Lenz gives you back EMF, which basically means it creates a voltage that counteracts. You were putting in this voltage as a fixed voltage, and as soon as you start changing the current in this winding, it produces a voltage opposite to that one. That one is opposite. So, and guess what? In a motor, to make it spin, you have multiple windings. So you're putting current on this winding, then that winding, then that winding, then that winding, then that winding. You're going from winding to winding to winding to get it to turn. And every time you put current on it, or put voltage on a winding, it's changing. And so we've got some problems with this electromagnetic field, that mainly because it's an inductor. All right, so that's one thing about a field. Two, about motors. Another thing to think about a motor. It's electromagnetic field, that's what you're trying to get. What's the first, there's three things mainly. What's the second thing that a motor is, that coil is as a circuit element?
Inductor.
Okay, we'll go with inductor. Yeah, next thing, exactly. So as soon as you coil up those wires, you made an inductor. So that coil wires is an inductor. Okay. So the bad thing about an inductor is, if you remember, is inductors don't like to change current, or they're a delay to current. Just like similarly, you can think of an inductor. It's an energy. What does it do with energy?
Stores it in a magnetic field.
Exactly. It's an energy storage device. Right? What's the other energy storage device component-wise that you guys have access to?
Capacitor.
Capacitor. Right. And so capacitors and inductors, both energy storage, and capacitors delay voltage, inductors delay current. Correct? Right? So what that means to us is, as you have a winding in the motor and you want a motor to actually develop current, because current is going to give you torque, it has to do this. Because it's an inductor, you have, let's see, current and time. At time 0, right here, it starts at 0, 0. As you apply voltage, it's not linear, is it? It's got a rise time to it. So what that means is when you first put current onto when it comes around, and let's say you're spinning the motor and you're going from one winding to the next winding to the next winding to the next winding, and that keeps pulling the magnet around until it makes its rotation. And it does that depending on the number of phases of the motor. It might take eight coils. Stepper motors take 48 coils to get around to do this. So you put current onto a coil, it's that phasing, it's time to move the rotor of the motor from here to here. So you put it on that coil. But it doesn't immediately give you any current because it takes a finite time for it to rise. And the one thing that you know is that torque is proportional to current in a winding, or it tries to be. And so you don't, when you first put current onto that winding, you don't actually get torque for a little while. Once you've got it, it's there. But this is kind of a problem that you have to deal with, is the rise time of the inductor. So what do motor manufacturers try and make? Do they put in high inductance or low inductance motors? They want high inductance because high inductance will give you lots of electromagnetic field and torque, right? So strong motor, but high inductance is also going to take forever to get up to that maximum torque. Low inductance is going to have a rise time. So this would be a low inductance motor. This would be high inductance.
Well, wouldn't that really depend on the application of the motor? If you need a fast reacting motor, but it doesn't have to be that powerful, wouldn't you switch to a low inductance motor?
Absolutely. It's exactly right. When you go to choose a motor, you decide, okay, here is the, it's a NEMA 23, it's 2.3 inches, and it's a single stack. You pick that one. You're not done just when you pick the size motor. That motor manufacturer is probably going to give you in a stepper motor, they're probably going to give you 5 or 6 different windings to choose from. And that's what you're choosing is, do you want high torque at low speed? Or do you want, which would be a high inductance motor, meaning they wound it a whole bunch of times, or did they wind it a lot less so that you have maintained more torque at the higher speed? It's exactly, you don't necessarily choose it directly. You're probably choosing it in the form of the speed torque curve has high torque, low speed versus the opposite. And that is what you're matching to your application. So it's one of the things you'll do when you go back and look at your concrete extruder, and you're going to say, all right, is that high speed or low speed? Well, what is it? What is it? Do you have a high speed or a low speed application?
Low speed.
Low speed, right. When you think of high speed in terms of revs per second, do a little math in your head. What kind of revs per second would a higher speed motor do? What are some motor speeds you've seen?
Like in hundreds, like 500 or something.
Yeah,
I think it's 2000.
2000 watts. Yeah, 500, 2000 watts. What are you thinking in?
600 revs per
Units?
second gives you 36
Revs per minute.
Yeah, like a 2000 RPM, right? But you got to pay attention. So what is an 1800? It's always the 60 in there. So an 1800 RPM motor is really what revs per second? Math in your head?
30.
30 revs per second. And how fast are we going?
1.5.
5, I think.
What is it? What's your spec?
1.5.
1.5. Right. So you have a high torque, low speed application. So when you go to pick that winding for that motor, that's one of the things you're going to see is for the same motor, some are wound differently than others, and they take different amounts of current, and so these are the choices that go into making a motor. Okay, so we've got one more thing that a motor is. Energy storage device, electromagnetic field. What's the one other thing? Here's a big clue. It's the bad thing.
Is it a heater?
Yeah. It's got resistance. Now, granted, it's not very much resistance, right? It's a coil of wire. What's the R? R is maybe, 1.6 ohms. I don't know. It varies all over. It could be 7 ohms. It could be point something. It's a piece of wire, but it has resistance. And what's the problem with having resistance when you run current through it?
Generates heat.
I squared R.
There
Squared
you
up.
go. Yep. And that's watts. So that's the problem with the motor, is that you want to run, the whole idea is to run current through it. But current squared starts adding up to watts. And so what limits, this is kind of an important thing to take away from this, is that no matter what motor they make and who makes it and how they wind it, the thing that ultimately limits the torque and speed, and torque times speed is power. So depending on whatever factor you're looking for, if it's more torque or if it's speed, or maybe you're after a certain amount of power for something, but what limits the motor, and this is any motor, I'll even write it out here. This is very key here. Put it in its own box. What limits any motor is its ability to what? What's the keyword? What's the keyword I want here?
Cool. Dissipate.
Create heat.
Right on. Right. It's not that it heats up. That's okay. How does it get rid of it? So what are your methods to get rid of heat out of a motor?
Fan on it.
How do you get rid of heat? What
Run
are
a
your
fan on it.
methods?
Add wings
Wings?
or fins. I mean, like
I'm all right with wings. What are you trying to do there? What heat transfer method are you doing when you add surface area?
Trying to do some forced convection, right?
Convection, right? So we got what are our three main types? How do we get rid of heat? We've got
convection.
right, convection, conduction, and radiation, right? I'm out of space, but you got it. So you got three methods to get rid of the heat of this motor. The big one that matters most is, which one did you guess is the most important one?
Convection.
Yeah, convection.
Good answer. Nope, it's conduction. That's your key. Most motors are designed to pull the heat out from the face of the motor. There's a really nice flat face there that you would put up against another machine surface, and you're going to pull that heat out. There's some, they put fins on them and try and do other things convection related, but really when you're using that's just doesn't work near as good unless you start blowing fans on it. By the time you start blowing fans on it, you're using energy to move air around, and you're not gaining in the energy equation at that point. So if you look at most motors, they have that really nice flat face. That's the heat conduction face. If you think about it, there's no reason for them to have this big flat face. Normally they could just have 4 tabs to mount it to, or just put a strap around it. But no, they give you that front face. That's for conduction. So when you design your stuff, you design a motor mount that's designed to pull that heat away and get it out of the motor. And just back to the tolerances and conditions, when you see a motor with torque, what's one of the conditions that they might assume that you're doing when they tell you you can get a certain amount of torque out of a motor?
Properly cooling it.
heat sinking, right?
Yep.
They're going to say, if you look down, it's one of those asterisk things like, okay, this is asterisk, assuming you have a heat sink with 80% contact and it's pulling, heat out the front versus just they would say it's free air or something like that. And so you keep that in mind as you are just setting a motor on your bench top and you're messing around with it. How much conduction's going on? Zero, right? You're relying on convection. So you're really going to heat up motors fast just sitting on the desktop while you're working on it in your proof of concept systems because you're not applying any conduction. And that's how they're really supposed to be used for the most part, okay? So this is what you're thinking about when you're trying to figure out which motor to use and how do you operate a motor, which parameters do you have control over. And you have some control over all of these when you pick a motor. One of the curves that becomes real important when you start to pick a motor, on one hand, it's kind of advanced if you go and we'll do this later in the semester, we'll start actually picking motors based on some of those parameters that I just gave you, inductance and constant current versus peak current. But for when you're just doing this now and you just need a motor that produces 12 foot-pounds, you just need to choose a motor, you're going to go try and find a manufacturer that's already done all the testing and tells you what amplifier to use to drive the current. So you're going to try and find something. A typical stepper curve has sort of a constant velocity or constant torque at first. And then the nature of this motor is it's a positioning motor. It's designed so that it can do positioning without you having to do any external feedback to it and keep track of the position, meaning it does what you tell it to unless it's completely inoperable or stalled. It works exactly, but it has a complicated magnetic structure. Part of this, so we have two parts to this region. This drop off is partly due to inductance, and part of it's due to complicated magnetics. And by magnetics, most of that is because it has this thing inside of it called teeth. They're machined teeth that are designed to focus that electromagnetic field. And so it has a fairly high stiffness. It's got physically, when you take it apart, when I get my stuff, I'll have this to show you, but physically it has machined teeth in it that line up. And when they line up, it gives a high stiffness around that tooth. And so it holds its position really well. And it's one of the things that makes it useful. We've got this area here is typically referred to as the constant torque region, not surprising. And what do you think this would be? What do you think is more constant as the torque drops off and you increase velocity? What is likely staying constant? Torque times speed equals, remember that from your mechanics somewhere?
Power?
Power, right. Right. So guess what this region is called? This is constant power region. Now later on, we're going to have just to draw this really quick. I'm going to draw it and then I'm going to get erase it just so you have it. That just so you know, if I had a servo like we'll do later, the speed torque curve would actually, of the similar size motor, would probably look more like this. It would be that big of a difference. So during the constant torque region, we're kind of limited by the current and getting rid of heat. But it doesn't have a complicated magnetic structure, and so it actually is way better throughout a much higher speed range than a stepper motor. So we're kind of limited to high torque and low speed with these steppers, which is perfect for this application. You're after high torque and fairly low speed. So this point right here, I'm going to actually put a number on it. So this is speed. Oops, wrong color. You got to get more practice at speed. I'm going to put a number on this. This is probably 10 revs per second. I'm going to say 2 to 10, something in there. Now, this depends on voltage, of all things. So you could have the same motor, and if they wind it differently, you could have one that has that curve. You could have another one that has this curve. You could have another one that has this curve. Actually, I drew that one a little bit wrong. Let me draw that one. It could have this curve. Those could all be the same size motor that are wound differently. The difference is inductance. And an inductor takes time to charge. So when you hit it with current, when you have that rise time of the inductor, at some point, like let's say when you get to this speed out here, when you get to 10 revs per second, right here at 10, this may be the point, this may be 10 revs per second. Over here might be the changing speed at 20 revs per second, meaning you have less time between winding changes. So over here, you only developed this much torque compared to when it slowed down, you had that much torque. And when it was going out here, when it was going 1 rev per second, you had time to develop full torque. This is, again, this is current versus time in a current in an inductor. So what you see is this curve kind of gets translated. This curve here starts to show up over here on that one. And so you can get various curves. They're higher torque and lower torque, and that's kind of how inductance matters on the speed torque curve. So what parameters do you actually get to change? Well, you choose voltage, right? And you control current. So the voltage, one of those where you choose what voltage is the system running at. It's not something that usually varies a lot. The thing that varies is how much current are you going to give it